Hello everyone and welcome to Lecture 8, Lines. First thing we do when we talk about lines is talk about the slope of a line, and we denote the slope of a line by the letter M. Typically in math, when we use the letter M, we're talking about the slope of a line. The slope of a line denoted by M can be computed by 1, choosing any two distinct points, x1, y1, and x2, y2 on the line. And then 2, plugging the values into the formula y2 minus y1 over x2 minus x1. And I might as well say this up front. I might as well say I need another marker. Memorize this formula for the slope if you don't have it memorized already. y2 minus y1, x2 minus x1, where x1, y1, and x2, y2 are the coordinates of any two distinct points on the line. So we take any two distinct points on the line and plug x1, y1, x2, y2 into this formula, and we get the slope. And just a remark, the slope of a line is a measure of how steep the line is. The greater in magnitude that the slope is, the steeper the line is. Now, let's do some examples. Okay, let's do an example. Here's a line, and I've picked 3 distinct points on the line. I don't need that many. I just need 2 distinct points on the line. But just for the sake of example, I'll take 3. And let's have this point be x1, y1, okay? So x1, y1 is the point 0, 2. And let's have this point be x2, y2, okay? So the point x2, y2 will be the point 3, 4. And using 0, 2 for x1, y1 and 3, 4 for x2, y2, the slope M is y2 minus y1 over x2 minus x1. Let's see, y2 is 4, y1 is 2, x2 is 3, x1 is 0, so I have 2 over 3. So we've computed the slope of that line. But for the sake of example, let's do it again. And this time, let's have the point x1, y1 be 0, 2. And we'll let the point 6, 6 be x2, y2. And we'll compute the slope of the line using these 2 points. Y2 is 6. Y1 is 2. X2 is 6. X1 is 0. And we get 4/6, but if we reduce this fraction, we get 2/3. Same slope that we got using this pair of points. But just for the sake of really driving home this point, let's let x1, y1 equal the point 3, 4. And we'll let the point x2, y2 be 6, 6. And we do our slope formula again, y2 minus y1 over x2 minus x1. Y2, that's, whoops, y2, that's 6. Y1, that's 4. X2 is 6. And x1 is 3. 6 minus 4 is 2. 6 minus 3 is 3. So again, we get the slope m equals 2/3. Now there's a point that we can get from all of this. And I'm going to make sure that before I erase what I have on the board, I make this point. And I'm also going to make sure that before I erase the board, I don't need what I have up here for anything else. You may have wondered about this. Does it matter which pair of points we pick on the line in order to compute the slope? And the answer is no. We used 3 different pairs of points on our line to compute the slope. And in each case, we got the same slope, m equals 2/3. So the slope of a line is independent of our choice of points x1, y1, x2, y2. x1, y1, x2, y2 can be any 2 points on the line. It doesn't matter. And we're always going to get the same slope. As far as the slope of a horizontal line is concerned, there are two special cases that we should look at. The first case is horizontal lines. And when it comes to horizontal lines, we have to remember something. The identifying characteristic of a horizontal line is that every point on the line has the same y coordinate. On a horizontal line like this, every point on this line has the same y coordinate. Now we look at this point. This is the y-intercept, and it intersects the y-axis at y equal b. So the y-coordinate of this point is b. Since this is a horizontal line, that means that the y-coordinate of every other point on the line is going to be b also. So this point, x is 1, y is b. This point, x is 2, y is b. And this point, x is 3, and y is still b. This point, x is 4, y is still b. This point, x is 5, y is still b. Every point on this horizontal line has exactly the same y coordinate as every other point on this horizontal line. And we look at where the horizontal line crosses the y-axis, this y-intercept. The y-intercept of a horizontal line, in this case b, is going to be the same as the y-coordinate for every other point on this horizontal line. Now, let's see what ramifications this has for the slope of a horizontal line. Here's a run-of-the-mill ordinary horizontal line, and we're asked to compute the slope of this horizontal line. So what do? We look at the y-intercept. It's b. That means that the y-coordinate of every point on this line is b. So let's pick at random 2 points on this line. Here and here. We'll call the x-coordinate of the first point x of 1. We'll call the x-coordinate of the second point x of 2. And since this is a horizontal line, the y-coordinates are all the same, b. And this point, b technically is our y sub 2. At this point, b technically is our y sub 1. B is the y-coordinate that is paired with x sub 1, so this is y sub 1. But y sub 1 equals b. And this point, this is the y-coordinate paired with x sub 2. But every y-coordinate on this point is b. So here y sub 2 equals b. And what do we get for slope? Slope equals y2 minus y1 over x2 minus x1. So that's b minus b over x2 minus x1 That's 0 over x2 minus x1, or just 0. The slope is 0. Now, let's just emphasize what it is that we just found out. Here's what we just figured out. If a line is horizontal, then the slope is 0. Does it work the other way around? If the slope of a line is 0, is the line horizontal? Absolutely. It's a two-way street. If the line is horizontal, the slope is 0. If the slope is 0, then the line is horizontal. This is our first special case as far as the slope of a line goes. Now let's look at the next special case, the second special case. Vertical lines. The identifying characteristic of a vertical line is that every point on the line has the same x coordinate. Let's take a look at an example. Here we have a vertical line, and the x-intercept of that vertical line is c. So right at this point, C0, the x-coordinate of the vertical line is c. And since this line is vertical, every point on this line has the same x-coordinate as every other point on the line. Now this point on the line has an x-coordinate of c. So every other point on this line has to have an x-coordinate of c also. Here the y-coordinate is 1. The y-coordinate is 1. The x-coordinate is c, the same as the x-coordinate of this point. Here, the y-coordinate of this point is 2. The x-coordinate of this point is the same as the x-coordinate of these 2 points, which is c. The y-coordinate of this point is 3. The x-coordinate is c. The y-coordinate of this point is 4. The x-coordinate is c. Every point on this line has the same x-coordinate. X equals c. Here's a vertical line. We're asked to compute its slope. So we'll pick 2 points on the vertical line. And you know what? Maybe that's a little bit more vertical. We'll pick 2 points on this vertical line. And we'll call this one CY1. And we'll call this point CY2. Now normally, if the y-coordinate of a point is y2, the x-coordinate that's paired with it is x2. So C is our x2 here. And normally, if we have a point y1 in the xy plane, the x-coordinate that's paired up with it is x of 1. So C is our x of 1. The x-coordinate of the point with y sub 1 is its y-coordinate. C is our x of 2. The x-coordinate of the point whose y-coordinate is y sub 2. And slope m equals y2 minus y1 over x2 minus x1. So we have what? Oh, come on. We have y sub 2 minus y sub 1. x2 is c. x1 is c. So we have y sub 2 minus y sub 1 over 0. And one thing that we don't do in math, it's a cardinal sin, we don't divide by 0. Anytime we divide by 0, the result is undefined. So what have we learned from this example? This is what we learned from the previous example. If a line is vertical, then its slope is undefined. Does it work the other way around? It sure does. If the slope of a line is undefined, then the line is vertical. So if a line is vertical, then its slope is undefined. If the slope of a line is undefined, then the line is vertical. They go hand in hand. Now let's look at some equations of a line. For the sake of trying to get an equation that has as its solution any point on the line, or every point on the line, let's suppose a few things. Suppose that a given line is neither vertical nor horizontal. These are special cases. We'll look at those in a little bit. So we have a line. It's not vertical. It's not horizontal. And suppose that the line has slope m, and that x1, y1 is a known point on the line. So we know the coordinates of this point, x1, y1. Okay, let's see what we can do with this information. Let xy be any other point on this line. So here's x, here's y, here's the point xy. We're going to use the slope formula. Here's the point xy. It's any point on the line other than x1, y1. And we're going to use the slope formula, and we're going to let this point xy play the role that x2, y2 plays in the slope formula. Now, normally, the slope formula is y2 minus y1 over x2 minus x1. But y is playing the role of y2 in this case. And x is playing the role of x2 in this case. We come up with m equals y minus y1 over x minus x1. And the first thing I'm going to do is multiply both sides by x minus x1. Cancel, 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 cancel. Now I just switch sides, that's all. What we've just come up with is the point slope form of the equation of a line. I'm going to write that again. Point slope form of the equation of a line. Now let's remind ourselves who the main characters are here. M is the slope. And what about this x sub 1 and this y sub 1? Didn't we start off by saying that x1, y1 were the coordinates of a known point on the line? So here, m is the slope, and x1, y1 are the x and y coordinates of a known point on the line. Let's work a few examples. First example, given that the equation of a line is y minus 3 equals 4 times x minus 2, name a point on the line, give the slope of the line. Well, the first thing that we do is we look at this and we say This fits a known form. Let's write down what we know. Okay, we've said just enough. The equation that we have fits this form. Y minus y1 equals m times x minus x1, where m is the slope and x1, y1 is a known point on the line. So let's take this known form of an equation of a line, and let's apply it to our example. Y minus y1, so this is y1, equals m times something, okay, this is our m, times x minus 2, x minus x1, this is our x1. So what do we know? Let's see, name a point on the line. X1, Y1 is 2, 3, is a point on the line. And 2, give the slope of the line. Well, that's this thing, isn't it? So just by taking the equation that we have and pairing it up with a known form, a known equation, that we recognize, aha, this is y1, this is x1, x1, y1 is a point on the line. Aha, this is the slope. Slope is 4. Now, before we venture on and do a few more examples, let me say something that I should have said before this example, and that is point slope form. Now, what I should have said before this example, but now is okay. I said earlier we have to memorize the slope formula, but we should also memorize the point slope form of an equation of a line. I'm not a big fan of memorization, but some things just have to be memorized. And this is one thing in math that we should know. Another example. Given that the equation of a line is y minus 6 equals 5x minus 7, name a point on the line, give the slope of the line. And again, this fits a known form. It fits the form y minus y1 equals m x minus x1. And we just match up the corresponding parts. y1 is 6, m, the slope is 5, x1 is 7. So, name a point on the line. x1, y1 equals 7, 6. The slope m equals 5. And we are done. Well, that was good. Let's try another one. Okay, given that the equation of a line is y minus 8 equals negative 2 times x plus 4, name a point on the line and give the slope of the line. And we compare this with a known form, y minus y1 equals m x minus x1. And we pair up corresponding parts. And it doesn't quite work. We want this to be x minus something so that it matches the form x minus x1. So what we're going to have to do is rewrite. We want to rewrite this equation so that it fits this form. So let's say y minus y1 equals m x minus x1. Here's the equation we were given, y minus 8. There's no problem there. We have y minus something. This is looking good. But next we have slope. We have something times x blah, blah, blah in parentheses. This is good right here. No problem. The only problem that we had is that we wanted this to look like x minus something, and instead it was x plus something. I want this to look like x minus something. How can I write x plus 4 as x minus something? Suppose I do this. Can I do this? X minus, not 4, but maybe x minus negative 4? X minus a negative 4, that is the same as x plus 4, isn't it? And now it fits a known form perfectly. So a known point on the line, x1 equals negative 4, y1 equals 8. and the slope m equals -2. Well, that wasn't nearly as much of a problem as we thought it would be. What do I have on the agenda? Do I have maybe one more example? Knowing me, I probably do. So let's do it. Given that the equation of a line is y plus 5 equals x minus 4, name a point on the line and give the slope of the line. So we'll try to see if this equation for a line fits a known form, the point slope equation of a line, which is y minus y1 equals m times x minus garbage. And x minus x1. Clearly, x1 is 4. We have x minus x1 and x minus 4. This much is fine. This part we have a plus sign here, but it needs to be a minus sign. I think we know how to take care of that. There's one more problem. Where's our slope? I don't see it. Well, let's try to rewrite this equation so that it fits this form. I have y plus 5 here, but I want it to look like y minus something. So how am I going to take y plus 5 and write it as y minus something? What do you think? If you're saying to yourself y minus -5, then you're right. Y minus -5 is the same as y plus 5, but now we have it written in the form that we want, y minus y1. And over here, there was never anything wrong with this. X minus 4, that's our x minus x1. So no problem there. But I'm supposed to have the slope here, m, multiplying what's in the parentheses. Do I have anything that's multiplying the contents of the parentheses here? You know, it's one of those things that's so obvious that we probably don't think about it. We do have a factor here outside of the parentheses, but we usually don't write it. And I'll tell you why. What's 1 times something? 1 times something is that something, right? And so usually when we write down something, We don't write it as 1 times that something. We just write it as something. For example, when we have 5, we don't write 5 as 1 times 5. We just write it as 5. And here we have x minus 4. That's the same thing as 1 times x minus 4. But usually we don't write the 1 here because 1 times, in this case, x minus 4, is just the same as x minus 4. But here's our slope. This was kind of a tricky one. So a point on the line, x1 is 4, y1 is negative 5. And the slope, m equals 1. Okay, we did some good examples. Let's go to our troublesome cases. Remember we said when we started this that we were dealing with lines that were neither horizontal nor vertical. Now let's take a look at the troublemakers and see how we express horizontal and vertical lines in equation form. Equation of a line, special cases, horizontal and vertical lines. Here's the bad news. Horizontal and vertical lines can't be written in point slope form. Think about it. Suppose, for example, that we had a vertical line and we want to write it in this form. Things look okay until we decide to plug in some number for m. And since we have a vertical number, there is no slope. It's undefined. So what on earth do we plug in here for m? There's nothing we can plug in for m to make this thing work. And we run into a similar dilemma with horizontal lines. Remember, with a horizontal line, the slope is defined. The slope is 0. So we plug 0 in for m, and this side of the equation is 0, which essentially means that y equals y1. In other words, the y-coordinate of every point on a horizontal line is the same as the y-coordinate of this known point on the horizontal line. And so that gives us an idea. If we try to use the point slope form of an equation of a line with a horizontal line, this is what we get. And when we move the y1 to the other side, what we get is, for every point xy on the horizontal line, the y-coordinate equals y1, the y-coordinate of the known point on the horizontal line. And that kind of makes sense. Remember how a horizontal line is characterized? The y-coordinate of every point on a horizontal line is the same as the y-coordinate of every other point on the horizontal line. So we can characterize a horizontal line completely just by saying, okay, pick one point on the line, see its y-coordinate. That's the y-coordinate of every point on the line, including the y-intercept. So let's take that and run with it. The equation of a horizontal line is y equals b, where b is the y-intercept. And a vertical line can be defined analogously. vertical line, the x-coordinate of every point on a vertical line is the same as the x-coordinate of every other point on the vertical line. So if the x-coordinate of, well, if the x-intercept of a vertical line is x equals c, then the x-coordinate of every other point on the line is x equals c. And this completely defines that vertical line. Give the equation of the horizontal line below. Okay, where does this horizontal line cross the y-axis? At the point 0, 3. The y-intercept is 3. The equation of the line y equal 3. Did that seem too easy? It did, didn't it? It seemed so easy that we were almost sure we'd done something wrong. But no, this is exactly how we express the equation of a line, a horizontal line. Y equals whatever the y-intercept is. And every point on this line is such that the y-coordinate is 3. Well, that was fun. Let's do another one just like it. Write the equation of the vertical line below. Well, the form of an equation of a vertical line is x equals the x-intercept, which in this case is x equals 6. The x-intercept is the point 6, 0, or just x equals 6. Since this is a vertical line, every point on this line is such that the x-coordinate is the same as the x-coordinate of every other point on the line. Every point on this vertical line has an x-coordinate of 6. And that in itself is enough to define this line completely. Time to introduce another form of an equation of a line. Slope-intercept form of the equation of a line. It's an alternative to the point-slope form. And I will say this, they're both very good forms. Sometimes one is easier to obtain than the other, but they're both very good. And we start off with the point-slope form of an equation of a line. Y minus y1 equals m x minus x1. And here, x1, y1 is a known point on the line. And when I say known point, it's a specific point on the line. So x1 and y1 are constants. M is the slope. That means that m is also a constant. So we take our point-slope form, and what am I going to do? You know what? I think the first thing I'll do is I'll take the slope m and I'll distribute it to both terms inside the parentheses. So we have y minus y1 is equal to mx minus mx1. And then I think I'm going to add y1 to both sides. So I'll have y equals mx plus y1 minus mx1. And I'll write that again up here. Whoops, 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 whoops. Y sub 1 here. There we go. Now, the interesting thing about what's in the parentheses is that m is a constant and x1 is a constant. So we have constant times constant is constant. Y1 is a constant. So we have constant minus constant, which is just a constant. This term is a constant. And we're going to call it B. Why do we call it B? Decades ago, maybe a couple centuries ago, somebody decided it would be a good thing to call this constant B. Y equals mx plus b. We already know that m is the slope. What about this thing b here? What is it? There's an easy way for us to find out what this thing is. And the way to do it is just to plug in 0 for x. And this gives us y equals m times 0 plus b, or just y equals b. So what does this tell us? It tells us that when we have this form of an equation of a line and x is 0, then y is b. Let's repeat that. When x is 0, y is b. Tell me something. If we have a point whose x coordinate is 0, where would we find it in the xy plane? If a point has an x coordinate of 0, isn't it on the y-axis? When x is 0, y is b. In other words, this line, the graph of this line, crosses the y-axis at the point y equals b. So b is the y-intercept of the equation y equals mx plus b. B, y-intercept, M, the slope, and oh yeah, let me not be remiss in mentioning that this is also one of those things that we have to memorize, the slope-intercept form of a line, y equals mx plus b. We gotta memorize it. But this isn't the Encyclopedia Britannica. It's just, what, 4 letters, y, m, x, b? We can do that. Here's a nice example. We have the equation of a line pretty much in, what would we say, point-slope form, with the exception of the fact that for this to really be in point-slope form, we should have x minus a negative 4. But it's close to being in point-slope form. And we're told to re-express this in slope-intercept form. So let's remind ourselves of what this is. Y equals mx plus b. We want to rewrite this equation in that form. So I guess the first thing I'll do is distribute the 3 inside the set of parentheses. And then, let's see, I want to end up with y by itself on the left. So I'm going to move this 3 to the other side. Now what else do we need? We need it in the form of y equals something times x plus some number. Something times x. Ha! We got it already. And just for emphasis, this is going to be our slope. And this is going to be our y-intercept. So slope, m equals 3. Y-intercept, b. Oh my goodness, that wasn't bad at all. That was not bad at all. As a matter of fact, that was so nice, maybe we ought to do another one. Why not, right? Express this line, which is approximately in point-slope form, and re-express it in slope-intercept form. Y equals mx plus b. I'm not sure what to do, so I guess what I'll do is I'll take the slope and distribute it to each term inside the parentheses. So that'll give me y plus 4 equals negative 4x plus 28 . I think the only thing to do now is just get y on the left by itself. So I'll subtract 4 from both sides. Holy moly, we're done. Here is our slope. And in a perfect world, we denote slope with an m. And here's our y-intercept, b. So we are done. Let's talk a little bit more about slope. Suppose we have two distinct points on a line, x1, y1, and x2, y2. And this is what it might look like. What's the distance from here to here on the x-axis? From here, x1, to here, x2. Isn't it just the difference of the x-coordinates, the larger minus the smaller? Now, what's the distance from here to here? Well, isn't the distance from here to here exactly the same as the distance from here to here? So that would be x2 minus x1, just the difference of the x-coordinates, the larger x-coordinate minus the smaller. And let me rewrite the coordinates of this point up here, just to get them out of the way. What's the vertical distance from here to here? Isn't this vertical distance the same as the vertical distance from here to here? And this distance is just the difference of the y-coordinates, y2 minus y1, the larger y-coordinate minus the smaller. So, this distance from here to here is y2 minus y1. Now you're probably thinking that I'm going to apply this to the distance formula, the distance between 2 points in the plane. But here I'm not. Remember what the slope is. It's y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are distinct points on the line. Well, what is y2 minus y1? Isn't it just the change in y coordinates going from, excuse me again, please. Isn't y2 minus y1 the change in y coordinates going from this point to this point? So we could express the numerator as change in y, and x2 minus x1, going from the point x1, y1 to the point x2, y2, isn't x2 minus x1 the change in horizontal distance going from this point to this point? It's the change in x, right? And our book also represents this as delta x over delta y. No, it doesn't. Forgive me, please. Our book represents this as delta y over delta x. So they say delta y, that's the change in y. Delta x, that's the change in x. But this is what the slope of a line is going from one point to another on the line. It's the change in y over the change in x. Remember, the slope of a line is change in y over change in x, going from one point to another on the line. And so we're given the exercise, graph the line that contains the point 4, 2 and has slope m equals 3/4. I'm not sure how to start this, so I'm going to do the only thing that I know for sure how to do, which is graph that point. Okay, that ought to be enough. And I'm going to graph the point with x coordinate 4 and y coordinate 2. So there's the son of a gun right there. X equal 4, y equal 2. Here it is. Now, in order to graph that line, I need to know another point on the line. And going from going from 4, 2, which is this point on the line, another point xy on the line, x will change by 4. Oh, you know what? Maybe I should write what this slope really tells me. Change in y and this 4 tells me change in x. So I can find another point xy on the line by making x change by 4 and y changing by 3. So let's see, if x changes by 4, going from 4 to 8, x just changed by 4. And now going from here, y is supposed to change by 3. So we're going from 2 up 3 units to 5. And we arrive at the point x equal 8, y equal 5. And that's our second point. Zingo, we have our graph. That's the easiest way to draw the graph of a line, given that we have a point and that we have the slope. Graph the line that contains the point 36, and it has the slope m equals -3/2. Well, the last example, the slope was positive. We didn't have to worry about a negative. There are two ways that we can look at this. M equals -3/2, change in y, over change in x. Or we can say m equals 3/-2, change in y over change in x. Either one of these two interpretations will be good. Now, as we did in the exercise before, the first thing we're going to do, because we don't know what else to do, is just plot this point. X equals 3, y equals 6. The point 36, x equals 3, y equals 6, is right about there. And now we need to get another point xy. And I can either choose this criterion or this criterion. Either one will get me where I want to go. So let's do this one. On second thought, no, I don't want to do that one. There's nothing wrong with doing this one, but it's less convenient. Forgive me, please. Let's do this one. So we get another point xy by doing the following. Go -3 units in the y direction. In other words, go 3 units in the negative y direction. The negative y direction is down. So go 3 units in the negative y direction. Beep, 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 beep. Okay. -3 units, or 3 units in the negative y direction. And then we're going to go 2 units in the positive x direction. positive x direction is toward the right. So 2 units in the positive x direction. And we have our new point. 6 minus 3 is 3. That's the y coordinate. 3 plus 2 is 5. That's our new x coordinate. Okay. And connect these 2 points, and that will give us our line. Now, before we go on to another observation or another example, let's milk this one for all it's worth. Let's look at the graph and see how it differs from most of the graphs of the lines that we've been working with so far. As we move from left to right along the graph, it goes downhill. And quite coincidentally, what was the slope of that line? Wasn't the slope of that line negative 3/2? Any line that has negative slope goes downhill from left to right. So then what about the graphs that go uphill from left to right? A line that goes uphill from left to right has positive slope. We should remember this. Lines that have negative slope go downhill from left to right. Lines that have positive slope go uphill from left to right. Let's draw a picture of that, okay? Look at this line right here. What would you say? Would you say this has positive slope or negative slope? Positive slope? Why? Because if we go from left to right, the line goes uphill. So this son of a gun has positive slope. Well, what about this line? What about the slope of this line? Negative, because it goes downhill from left to right. And if that's what you said, you're right. And let's make one more observation by doing an analogy. On the number line, what number on the number line is between the negative numbers and the positive numbers? What number on the number line lies right between the negative numbers and the positive numbers? As a matter of fact, this is the only number that's neither positive nor negative. This number, which is neither positive nor negative, is the boundary between the negative numbers and the positive numbers. And what number is that? Well, let's see. Here's the number line. -2, -1, 0, 1, 2. So 0 is the number on the number line that's in between the negative numbers and the positive numbers. 0 is the only real number that's neither positive nor negative. Now let's apply this to slope. This line right here, this line right here, it's not going uphill, it's not going downhill. It's not going uphill, so it's not positive. It's not going downhill, so it's not negative. So what's the slope? The only slope that could be between the positive slopes and the negative slopes. Yeah. 0 slope. Here's a good example. Parallel lines. Two distinct lines are parallel if they have the same slope. And note, parallel lines do not intersect. Here are two distinct lines, and I claim they're parallel. They both have slope 2/3. Let's graph the first one. It's in slope-intercept form. So the slope is 2/3. The y-intercept is 2. So I'll graph this point. Here's my y-intercept. And my slope is 2/3, which means I can find another point on this line by going 3 units in the positive x direction and then 2 units in the positive y direction. So that puts me at what? 3, 4. And just to make sure that these lines end up looking parallel, let me use a straight edge to plot it. Okay. Now, let's plot this other line. Again, it has slope 2/3. This time the y-intercept is 4. So I'll plot the y-intercept at y equals 4. And then to get another point, I'll go 3 units in the positive x direction. Ooh, right here. 3 units in the positive x direction. And 2 units in the positive y direction. And that puts me at what point? Y is 6 and x is 3. Okay. And let's graph that son of a gun and show that these two lines are in fact parallel. Beautiful, isn't it? So any two distinct lines are parallel, they never intersect. And I guess if we talk about parallel lines, I have in my notes, I need to do one more example of parallel lines. Okay, another example having to do with parallel lines. Find the equation of the line that is parallel to the line y equals 2x plus 3, and that contains the point 1, negative 2. If the lines are parallel, then they both have the same slope, right? And we know what slope this line has. This line has slope 2. And since both lines are parallel to one another, they both have slope 2. The line that we're asked to find has slope m equal 2, and it contains the point 1, negative 2. Let's see. We know the slope and we know a point on the line. We know a point on the line and we know the slope. Point on the line, we know the slope. I got an idea. Let's use the point slope equation of a line. When we're trying to find the equation of a line and we know a point on the line and we know the slope, that's the form of the line that we go to. Y minus y1 equals m x minus x1. M is 2, x1 is 1, y1 is negative 2. Oh, we just plug those numbers in, turn the crank, and we got our equation. Y minus y1, y1 is negative 2, equals slope, and that's 2, x minus x1, x1 is 1. Now, you know what? If we leave it like this, it's not simplified. And my math lab may not like this. But if we leave it like this, there's something nice about it. What's nice about it is this. We can look at this equation, and we know two important things about this line by inspection. We look at this equation and we go, aha, the slope is 2. And we look at this equation and go, this equation contains the point 1, negative 2. So if we left it in this form, my math lab probably won't like it, but it's not a bad form because we can look at this thing and instantly take away two important features of this line. It has slope 2, and it contains the point 1, negative 2. And let me just clean this up a little bit. Y plus 2 equals 2x minus 1. This is probably the form that my math lab is going to appreciate. One more topic and we're done, everybody. Perpendicular lines. Two lines are perpendicular if the slope of one is the negative reciprocal of the slope of the other. What? Okay, take the slope here, negative 1 over m sub 1. The slope here is negative 1 over m sub 1. And this is the negative reciprocal of the slope of this line. The slope of this line is m sub 1. If we take the reciprocal of this slope, we get 1 over m sub 1. And if we take the negative reciprocal of this slope, we get 1 over m sub 1 with a negative sign in front. Clear as mud? Let's look at an example. But before I do, let me say something about the graphic significance of perpendicular lines. The graphic significance of perpendicular lines is that they intersect at a right angle. So here's the first line, y equals m sub 1x plus b. Here's the second line, y equals negative 1 over m sub 1x plus b. They intersect at a right angle. Now let's look at some examples. Here's an example. Two lines in slope-intercept form, and the y-intercept of each point is 3. I made things easy on myself. Here's the y-intercept of both lines. And notice that they're perpendicular. The slope of this line is negative the reciprocal of the slope of that line. Take the reciprocal of this line, it's 1/2, and then multiply it by negative 1, and you got the slope of this line. And I claim that they're perpendicular. So let's see. Slope 2 the first line has a slope of 2. So we can say that this is 2 over 1 change in y over change in x. So if we start here at the y-intercept and change 2 units in the positive direction, that's our change in y. And then we go 1 unit in the positive x direction, and we get another point on the graph. Now, let me see if this looks, this looks pretty good. Let me draw that line. Okay. Y equals 2x plus 3. Now let me draw this line. The slope is negative 1/2. And I can look at this as negative 1 over 2. Change in x. There used to be an e in change. I don't know when that stopped being the case. Change in x is 2. Positive 2, so we go positive 2 units to the right. Beep, 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 beep. Okay, 2 units. And now we're going to go -1 units in the positive y direction, or 1 unit in the negative y direction. So how do we go in the negative y direction? The negative y direction is down, so we go like this, 1 unit down in the negative y direction, and we get our next point. Yeah, that looks good. That looks very good. And now let's plot this son of a gun. Now are these two lines perpendicular or what? Are they perpendicular or do pigs fly, huh? What a good graph. Let's do one more example with perpendicular lines. New example. Give the equation of the line that, first of all, contains the point 2, 2. And second of all, is perpendicular to the line y minus 4 equals 3, x minus 12. Well, the slope of this line is 3. The line that we want is supposed to be perpendicular to this line. So the line that we want should have slope, which is the negative reciprocal of this slope. We want the line that has slope m equals -1/3, and it has a point x1, y1 equals 2, 2. So let's see. We know a point on the line and we know the slope. We know a point on the line and we want the slope. Point, slope. Let's use the point slope form of an equation of the line. So we want y minus y1 equals m x minus x1 x1 is 2, y1 is 2. Oh, this is going to be easy. Y minus y1, that's y minus 2, equals m, we'll come back to this later, x minus x1, x1 is 2. Now the slope. Oh, son of a gun. Our slope should be -1/3. And you know what? That's it. This is the point slope form of the equation of the line, which is a very good form to put the line in. So we will just take it like this and say, I'm done. And we're done. That was a long lecture, wasn't it?